Okay. So today we will discuss macroscopic state and microscopic state. For that, we first consider a container of ideal gas molecules of volume V containing this container contains Avogadro number of molecules. Okay. So this is the container. This is the container. Okay. So we consider one container contains ideal gas and the volume of the container is V, and in that container we have kept Avogadro number of molecules. So this is a description of macroscopic system. Okay, so macroscopic systems are characterized by few variables like pressure, volume, temperature, etc. So we can observe what is the pressure here or what is the temperature here, etc. But the description in terms of microscopic parts requires the specification of the state of each and individual particle. So while we discuss about macro state, there we did not consider the what is the contribution to the pressure of each and every particle. Okay, here. But description, if you in terms of microscopic part, requires the specification of the state of each and individual molecule. Now, the number of molecules we consider here is in the order of Avogadro's number, and for each particle or molecule we need to know at least 3 position coordinates and 3 momentum coordinates. Okay. So, total 6 variables we need to know for each particle, and we have used Avogadro number of particles here. So, typically we need 6 times 10 to the 23 variables. Thus, to specify the microscopic state of the system, it is convenient to work on in 6 n-dimensional space of coordinates and momentum of n particles. This 6 n-dimensional space is called phase space of the system, and microstate is simply a point in the phase space, and the macroscopic state on the other hand corresponds to a large number of microstates, and it represents a volume in the phase space. Okay. So we have we can see it in this plot here. Now, if we specify the total energy, suppose total energy say E of the n particle system, it allows for a large number of microstates corresponding to this macrostate. Okay. So as we see that we have 6 n-dimensional space here. Okay. So here we plotted 3 n number of momentum coordinates versus 3 n number of position coordinates, and macroscopic state is only a point in that phase space. On the other hand, the macroscopic state, it's a volume in the phase space. Okay. So if we consider a particular microscopic state of the system and watch how it evolves in time, we will be obtaining phase trajectories. So what is phase trajectory? Okay, so if we consider a particular microscopic state of the system and watch how it evolves in time, we will be obtaining phase trajectories. Now we will here consider 2 examples for better understanding of macrostate and microstates. Okay. Suppose we are flipping 2 coins. Okay, so one possibility is first coin comes with head and second coin comes with tails. So this is the first occurrence here. Then next occurrence is first coin we get tails, and for the second coin we get heads. So for this macrostate, means 1 head and 1 tail, we have 2 microstates. Okay. First we have head, then tails, or tails heads, like this. Similarly, for macrostate HH, means for both coins if we get heads, so for this macrostate we have only 1 microstate. Okay. So for this one, for HT or TH, we get 2 microstates. For this one, we get 1 microstate, HH case, and we can also get tails, both the coins, for both the coins. So, for this one we get, for this macrostates we define by Tt here, we get 1 microstate. So, we have total 3 macrostates. What are those macrostates? One head, one tail is 1 macrostate, both the heads is 1 macrostate, and both the tails is the third macrostate. And how many microstates we have? We have 4 microstates, because macrostate HT, head tail, contain 2 microstates, okay, like HT or and TH. Okay, so next we take another example. Okay, so we have suppose 4 walls, and then we have 2 rooms or 2 baskets, whatever you say. Okay, and these balls, they are identified by different colors. Okay, now if I ask you, you put 4 balls in different manner. Okay, what are the possibilities? First possibility is all 4 balls are in the first room, and there is no ball in the second room. So this is 1 macrostate possible. Okay, so this is microstate, 1 microstate. Okay, like this. Then we can have blue, red, and green ball in one room, and a red ball in second room. And now we can change the ball, means 3 balls in one room and 3 ball in first room rather, and 1 ball in second room. Okay, so for this kind of arrangement we get 4 microstates. Now we can have, in both rooms we can have equal number of balls, means 2 2. Okay, now if we rearrange the balls, okay, so we get 6 different possibilities here. Okay, and then in the fourth case, suppose we put 1 ball in first room and 3 balls in the second room. Okay, and for this case we get 4 different possibilities. And the last case, the first room is empty and the second room contains all the 4 balls. Okay, so how many macrostates we have now? We have 5 macrostates. Okay, and how many microstates are there? We have 16 microstates. Like for the first macrostate, we have only 1 microstate. For the second macrostate, we have 4 microstates. For third microstates, we have 6 microstates. For fourth macrostates, we have 4 microstates, and for fifth macrostate, we have only 1 microstate. So now we understand what is macrostate, what is microstate. Next, we start with Boltzmann factor. So now we discuss Boltzmann factors. Okay. Okay, all of you know Schrodinger equation. Okay, so the Schrodinger equation for n-body system this Hamiltonian operator H operating on psi j gives energy value Ej like this. Okay. So basically what we considered here, we considered a cubic box. So we considered a cubic box containing n number of ideal gas molecules, okay, and so we have one container here and the volume of the container is V, and edge length of each edge of this box is A, suppose. So, for this kind of system, so this is our system here we are considering. Okay. So, we are considering a system. Okay. The system is like a cubic box containing n number of ideal gas molecules and volume of the container is V and edge length of the box is A. So, V is nothing but A to the 3, right. And for this kind of system, the Schrodinger equation we can write H psi equals to E psi. Okay. And here J is 1, 2, 3, etc. It varies like this, and these are microstates. Okay. Now for this special case of ideal gas, since ideal gas they do not interact with each other, we can write E j, the function of n and v. We will discuss why E j depends on, or how does E j depend on n and v, number of particles and volume v. Okay, and if you go back and check, okay, so H psi j equals to E j psi j, and this psi j, this 1 to psi j in the bracket 1 to 3, they represent the coordinate of particle 1, coordinate of particle 2, coordinate of particle 3, etc. Okay, now, so E j is like this. So, if we say the psi j, H psi j equals to E j psi j, this is our equation 1, and we can say this is our equation 2. Okay. What are those epsilon 1, epsilon 2, etc.? Okay. So, epsilon 1, epsilon 2, etc. are the individual molecular energy. Okay. So, in the expression of E j means E j equals to epsilon 1 plus epsilon 2, this expression 2, it contains n number of terms, right, number of particles, it depends on number of particles. So, E j depends on number of particles. Okay. So, that is how the n dependency of E j comes here. Okay. And we can add them, the molecular energy levels, because epsilon 1 plus epsilon 2, etc., because we are considering here ideal gas. Now, for example, for a monoatomic ideal gas, okay, if we consider a monoatomic ideal gas in that container, okay, in the container presented above, presented here or considered here, considered here, if we ignore the electronic states and focus only on the translational states, then E's epsilon j's are just the translational energy given by so we consider three-dimensional box. So epsilon nx comma ny comma nz is h to the 2 by 8 m a to the 2 like this. Since we consider a three-dimensional box, we get this expression. So this is related to the particle in one-dimensional box. So this is for energy value for energy expression for particle in three-dimensional box. Okay. Now, how does the V dependency comes? We discussed how does n dependency of Ej, Nv it comes. Now, the V dependency comes. So, if we see this expression here, we see that there is one term called a to the 2. So, in the above expression, we have a term a to the 2 in the denominator, right? Okay. And we know, and a is nothing but v to the 1/3, right? We consider cubic box. Okay. So it says, so or it depicts the volume dependency, V dependency, of Ej. So now we know how does Ej depends on n and depends on V. Okay. So what is our goal? Okay. So our goal is to know our goal. So what is our goal? So we want to know the probability that a given or that a system will be in the jth state having energy or with energy Ej. Okay. So we want to know the probability, because if we know the probability, then we can calculate the average quantity, right, with the help of the discussion that we discussed in the last class. So to do this, or for this, we consider a huge collection of systems in contact with the heat reservoir at a temperature T, Each system has the same values of a number of particles, volume and temperature. Okay. But is likely to be in different quantum state consistent with the values of N and V. Okay, such a collection of systems is called an ensemble. Okay, so for this actually what is our goal? Our goal is to know the probability that a system will be in the jth state having energy Ej. For this what we consider? We consider a huge collection of systems in contact with a heat reservoir at a temperature T. Each system in that collection has the same values of N, V and T, but is likely to be in different quantum state consistent with the values of N and V. Such a collection of systems is called an ensemble. Okay. So, what is the definition of ensemble? So, next we will just define ensemble. Okay. So, what is the definition of actual definition of ensemble? So, it is an idealization consisting of a large number of mental copies, sometimes infinitely many. Okay, so we consider many or a huge or large number of mental copies, okay, of a system considered all at once, each of which represents a possible state that the real system might be in. So, what is the definition of ensemble? Ensemble is an idealization consisting of a large number of mental copies, sometimes infinitely many of a system considered all at once, each of which represents a possible state that the real system might be in. Okay. So, since we consider constant in Vt, so we are basically describing canonical ensemble. Canonical ensemble. So, in canonical ensemble, number of particles, volume of the system and temperature are fixed. Okay. So, now basically what is ensemble? If we represent pictorially, we get like this. So, these are the mental copies of our system, and they all are having constant NVT, and the whole thing. Okay, so let me draw it again a little bit better manner. So, we have like this. Okay, so all are having in same number of particles, volume and temperature fixed, etc. Okay, so we have heat reservoir here. And whole thing, if we just putting one insulator here, so isolated from whole thing is isolated from the surroundings. Okay. So, we have insulator, thermal insulator. So, these are all mental copies. Okay. So, our goal is to find a state J having energy Ej, and for that what is the probability. Okay, that is our goal. Okay. So, we define, say, Aj, we are defining one quantity Aj, which is number of systems in the state J with energy E. Okay. So, our goal is to calculate. Okay. So, how many systems are there in the J state having energy Ej, that we called Aj. Okay. And capital A represents total number of the systems in the ensemble. And this A is very large, usually very large, very large number we consider. Okay. So, we defined two quantities Aj and A, where Aj is the number of systems in the state J with energy Ej, and capital A is the total number of the systems in the ensemble. Okay. Okay. So, now the relative number of systems in the states with energy E1 and E2 must depend on U1 and E2, right. Okay. So, you can write A2 by A1 is, it depends on U1 and E2. Okay. Okay. So, what is A2 and A1? Okay. So, A2 is the number of states having energy E2, and A1 is the number of states having energy E1. Fine. Okay. Now, since energy is a quantity that depends or that must always be referred to a zero energy zero of energy the dependence on U1 and E2 in equation suppose this is our equation 3 not 1, in equation 3 must be of the form A2 by A1 is function of the difference in their energies. Okay. Because energy is a quantity that must always be referred to a zero of energy. Okay. We need to consider one zero of energy. Okay. So, the dependence on E1 and E2 in equation 3 must be of the form this. Okay. So, suppose we are calling this one as equation 4. Okay. Okay. So, now this equation 4 is true for any two energy states, Thus, we can write that A3 by A2 equals to this function of E2 minus E3 and A3 by A1 is function of E1, the difference in E1 and E3. Or again, A3 by A1 is nothing but A2 by A1 times A3 by A2. So, it says f E1 minus E3 is right. So, suppose this is our equation number 5. Okay. This equation 5, the above equation 5 is very similar to e to the x plus y is e to the x times e to the y. So, we can write, so A2 by A1 is nothing but e to the beta E1 minus E2. Okay. So, this is our equation number 6. This is our equation number 6. So, in general, I heard beta is a constant. And we will later see that beta is inversely proportional to absolute temperature. Later we will see, or we can write beta is 1 kb T, where kb is the Boltzmann's constant. Okay, that data we will prove it. Okay. So, here beta is a constant for time being, you assume. Okay. So, in general, equation 6 can be written as AM by AN is e to the beta EM minus AN, right. Okay. Or we can write AM is, sorry, this is AN minus EN minus EM. So, in general we can write AM is proportional to e to the minus beta times EM. Okay. Or we can write AM is nothing but C times e to the minus beta AM. Okay. Since M is a dummy variable, so we can write AJ is nothing but C times e to the minus beta EJ. Okay. So, for jth state this is also valid, where C is a proportionality constant. So, what is the value of C? We will see it. Okay. So, what we get? We get AJ is C times e to the minus beta EJ. Okay. Now, what is the value of C? Of C, the proportionality constant. Okay. So, sum over J AJ is nothing but A, total number of states, right, and is C times J e to the minus beta J B. Or we get C is A by sum over J e to the minus beta j Np. So, if you substitute the value of C in above equation of Aj, we get, so we get Aj is A e to the minus beta Ej by sum over j e to the minus beta Ej or we can write Aj by A. So, what is Aj by A? We have Aj number of states having energy Ej, and capital A is the total number of steps, total number of states. So, what is Aj by A? Aj by A is nothing but the probability of jth state having energy Ej. So, Pj, if we say probability, this is probability of state J having energy Ej. So, probability depends on NV beta, we can write e to the minus beta Ej NV by sum over j e to the minus beta Ej Np, and this j is sum over states, right. So, what we obtained so far? We obtained Pj Nv function. So, Pj is function of Nv and beta is e to the minus beta Ej by sum over j e to the minus beta Ej Np. So, what was our goal? Our goal is to get the probability of state J having energy Ej, that we arrived at. So, this is the expression for that. Okay. And the denominator we have sum over j e to the minus beta Ej and V sum over j is sum over states. We define it as Q, and this Q is known as canonical partition function. Okay. So, the expression of Pj now reduces to so now we have obtained the value of Pj, okay, probability of state J having energy Ej. Since we have obtained the expression for Pj, we can calculate various thermodynamic quantities. Thank you.